fundamentals of material forming. I am Dr. Sanjay Kumar Gangurde, Professor, Department of Production Engineering, KK Wag Institute of Engineering Education and Research. In this video, we will learn about classification of material forming process, stress strain diagram, that is engineering stress and engineering strain, true stress and true strain. Then we will discuss about work done in elastic and plastic region, theory of plasticity, yield criteria for ductile material. There are two criteria generally used for the analysis: von Mises criteria and the Tresca criteria. Effect of temperature and strain rate on the deformation and concept of the formability with formability diagram. There are different types of manufacturing processes. The manufacturing processes are subdivided in the following groups. The first group, it is shaping, that is casting is the process in which the molten metal is poured into the cavity, allow it to solidify. Then this casted part, it is to be taken out from the mold cavity after cooling the casted product. So there are different types of casting process: sand casting, investment casting, centrifugal casting, continuous casting, etc. Then other main group, it is forming process in which the material is plastically deformed. Plastically deformed means permanently deformed. Then third group, it is machining, that is material removal process. Chips are formed during the machining process. Then joining, we are adding or joining one material with another material. So welding is welding, soldering, pressing, these are the joining process. Then coating, we have to apply some coats on the material finished products. Coating may be zinc coating, silver coating, gold plating, and another group, it is modifying material property. So in this video we will discuss about the forming process. So forming process in which the material is formed or deformed by plastic or permanent deformation, and in this process the volume remains constant. So the basic principle of forming process is that there is no material removal. That means the volume before deformation remains constant and same before after deformation. So the forming processes are classified into different categories. The first category, it is direct compression process. Then second category, indirect compression process. Third one, it is tensile process, forming by tensile force, forming by bending, and forming by shearing process. So let us see the first one, direct compression process. So one of the most important process, that is the forging. It is the direct compression process. The material is deformed with the help of external compressive force. So therefore it is to be termed as direct compression process. So material, it is deformed between two dies, upper die and the lower die, and the deformation is carried out by direct compressive force. Then the rolling process, in which the material, it is deformed under the pressure of roll. There is upper roll as well as bottom roll, into which the material is deformed. Then the indirect compression process. Wire drawing is indirect compression process. Now you can observe the wire or rod is pulled through the die by applying tensile force, but the deformation is carried out by the compressive force. The arrow indicates the compressive force and the material is pulled by tensile force. Then extrusion process, the material is compressed. Then there is forming by tensile force. There is stretch forming. The material it is pulled with the help of punch. We will discuss this stretch forming and with the help of tensile force you can form the material. So stretching is there. So tensile force you are applying. Then bending. The bending force it is applied to deform the material. And there is a shearing forming by shearing. So there are different sheet metal working operations: punching, blanking, shaving, trimming, perforating. These are the different press working operations, and the operations are shearing operations. Now we will discuss about the stress strain curve. With the help of this stress strain curve, we will discuss about engineering stress noted by sigma E and engineering strain. It is also called as nominal strain, conventional strain or linear strain. It is denoted by small letter E. The engineering stress, it is nothing but the ratio of applied load to the original cross-sectional area. Engineering strain is the ratio of change in length to the original length. So we are having stress strain diagram. On y-axis you have to represent stress, on x-axis strain. This is the stress strain diagram. Up to elastic limit, the stress is directly proportional to strain. This is nothing but the Hooke's law. The material obeys the Hooke's law, that is stress is directly proportional to strain. So sigma E is directly proportional to E up to the elastic limit. Sigma 0 here represents the yield stress, and the ultimate tensile strength it is shown, and there is a fracture strength. So this is the engineering stress for the ductile material. Engineering stress versus engineering strain. Generally this graph it is plotted after carrying out simple tensile test of a specimen. Then true stress and true strain. So true stress it is denoted by sigma t, and true strain it is denoted by letter epsilon. True stress it is nothing but the ratio of instantaneous load at any point to the actual cross-sectional area at that particular instant. And true strain epsilon, it is defined as the ratio of the instantaneous change in length to the length at that instant. So d epsilon, it is nothing but the finite increment of the deformation from original length LO to LI. So epsilon can be represented as L integration of LO to LI. D epsilon, it can be represented as integration from LO to LI dl by L. So you can have log of Li by LO. As the material forming it is based on volume constancy principle, it is equal to log of A0 upon AI, as the volume of the specimen is constant before deformation and after deformation. So A0 into L0, it is the volume before deformation, and LAI into LI, it is the volume after deformation. So you can write Li by LO, it is equal to A0 by AI. So this is the stress strain curve, conventional curve, that is of engineering stress versus engineering strain, and when you are plotting true stress versus true strain curve, it appears like this. So we will take one example later on this. So what is the relationship between engineering strain and the true strain? So linear strain at an instant I is linear strain E equal to dl by LO, that is Li minus LO, that is change in length, divided by LO. You can write E, it is equal to Li by LO minus 1. So or Li by LO, it is equal to E plus 1. So taking log on both the sides, log of Li by LO, it is equal to log of E plus 1. So epsilon equal to log of E plus 1. In previous slide we discussed about this. Epsilon log of Li by LO equal to log of E plus 1, and epsilon it is equal to log of E plus 1. So this is the relationship. True strain epsilon, it is equal to log of E plus 1. Then relationship between engineering stress sigma E and true stress sigma T. So engineering stress, it is given as applied load divided by original cross sectional area, and true stress, it is given as load at any instant divided by cross sectional area at that instant. But in material forming, volume remains same before deformation and after deformation. So A0 into L0, it is equal to AI into Li. So you can write AI A0 into LO by Li. We know that Li by LO, it is equal to 1 plus E. Therefore, AI, it is equal to A0 by 1 plus E. Substituting this in true stress equation. So sigma T, it is equal to P by A0 by 1 plus E. So you can write this P by A0 into 1 plus E. So sigma T equal to sigma E into 1 plus E. So this is the relationship between true stress and engineering stress. Let us take one problem related to this. A tensile specimen of 12 mm diameter. This is the original dimension of the specimen, and the length of the specimen is 50 mm, is subjected to 400 Newton load. At that instant, the gauge length is obtained 64 mm. Assuming the deformation is uniform to this point, compute true stress and true strain, and second, determine the diameter at the instant. So length is increased from 50 mm to 64 mm. That means the cross sectional area is reduced. Cross sectional area is reduced means the diameter it is reduced. The initial diameter it is 12 mm. The final diameter you are getting at that instant, it should be less than 12 mm because its length increases. So given data it is original diameter 12 mm, original length 50 mm, load 400 Newton, length at that instant 64 mm. We have to calculate original cross sectional area. So it is 113.1 mm square. Engineering stress, it can be found out 400 by 113.1. So it is found out 3.53 Newton per mm square. Engineering stress, change in length divided by original length, 64 minus 50 by 50. So engineering strain you have calculated 0.28. From this engineering stress and engineering strain, as you know the relationship between true stress and engineering stress, as well as engineering strain and true strain, we can find out true stress and true strain. So this is the data. True stress can be found out. Sigma t, it is equal to, this is the relationship. So sigma e, engineering stress 3.537, engineering strain 0.28. You can find out true stress, that is 4.527 Newton per mm. True strain epsilon can be found out equal to log of 1 plus e. It is 0.28. True strain you can find out 0.2469. Or another way, true strain epsilon can be found out log of Li by Lo. So it can be found out 0.2469. So diameter at that instant, true stress sigma t, it is equal to P by Ai. Sigma t you have calculated, P it is known to you. So P it is 400, sigma t 4.527. Cross sectional area at that instant 88.35 mm square. So diameter at that instant can be found out by putting all these values in the formula. You can find out the diameter at the instant, that is 10.61. Now from original diameter was 12 mm, original length was 50 mm. So volume your before deformation and after deformation remains constant. So original diameter is reduced and the length it is increased after the deformation. So diameter at that instant it is 10.61. So this is about the true stress and true strain, and we discussed about the various stresses and strain, and we discussed about stress strain diagram.